Okay folks, here we are with lesson 3, solving trig equations part 2. There's going to be a few parts because there's lots of different types of trig equations, different families of equations, and you need to know each one of them. You need to be familiar with each one of them. The one we're looking at today involves that identity, tan theta equals sine theta over cos theta, but it won't necessarily be as obvious as that. You've got to look for it. So without more of ado, let's crack on and get the job done. So here we go. And you're looking for an equation which involves sine theta, cos theta, and no constant. Let me explain what I mean. Here's a set of equations from the exercise, and each of them have a sine theta and a cos theta, but no constant. And by constant, these root 3's here, and the 3 there, and the 4 there, and the root 2, etc., they're coefficients, they're not constants. So there isn't a separate constant in any of those 6 equations that you can see. Similarly, in exercise 10e, there are no constants. There are coefficients here, the 4, the 5, the 2. And these here are in the angle, they're part of the angle, so that's not what I mean by a constant. What I do mean by a constant occurs in the Pure 2 book. We have a look at this question with sine and cos in, looks very similar to the previous ones, but what I mean by a constant, there it is, okay, separate from the sine and cos term, separate from the sine and cos term, separate and separate is the constant. So we're looking at ones with the sine and cos term, but no constant. So here's an example. And the first thing we do is, if we divide by cos theta, we end up with that. Note on the right hand side, I've divided the 0 by cos theta just for completeness. And then the root 5 sine theta over cos becomes root 5 tan. In the second term, the 2 cosines cancel out to leave subtract 2, and the right hand side is 0. Therefore, rearranging that gives me tan theta equals 2/5. And now that's the equation I wish to solve. Solve the equation tan theta equals 2 over root 5 between 0 and 360. Step 1, calculator, inverse tan, 41.81 degrees. Step 2, cast diagram. 41.81 degrees is 41.8 to the horizontal axis. Where else is tan positive? It's in the yellow quadrant. 41.8 degrees to the x-axis, and you'll find that that angle is 221.8 degrees. Those are our solutions. In example 2, note the two angles 2 theta minus 30, 2 theta minus 30 are the same. They have to be. If we divide by cos of 2 theta minus 30, we end up with that. Looks a bit complicated, but the first term, sine over cos, is just tan. In the second term, the cos term cancels out, so you're going to be left with subtract 2, and the right hand side is 0. So we're left with that equation, and tan 2 theta subtract 30 equals 2. That's what we're trying to solve. And because the angle is not a straightforward angle, we do what we were doing yesterday, simplify the angle to equal y. Now we have an equation of tan y equals 2. Step 2, adjust the domain. We've got a domain of theta. We want to adjust that so it reads 2 theta subtract 30. So the first thing is I multiply by 2, and then I subtract 30. And therefore, our new question is basically solve the equation tan y equals 2 for y values between -30 and 690. So our next step is the calculator. Inverse tan of 2, 63.43 degrees. Now we use the cast diagram. You should be familiar with this by now. 63.4 degrees to the x-axis. Where else is tan positive? In the yellow quadrant. So 63.4 degrees to the x-axis there gives us an angle of 243.43 degrees. Now note, we need y between -30 and 690, and our two angles are 63.4 and 243.4. So we can add 360 degrees to each of these and still fit two more angles in. So here now we have our 4 solutions for y. But our final step is to find that in terms of theta. We don't want to know what y is, we want to know what theta is. We're remembering that y equals 2 theta subtract 30, and we have our 4 solutions there. If we add 30 to both sides, we end up with 2 theta equals those 4 solutions, and then if we divide by 2, we have our solutions for theta. So the exercises that I want you to have a look at are in the Pure 1 book, exercise 10D, etc. You can read it there, and exercise 10E. Now you might want to pause the video while you do those 2 questions, because there's a little bit more coming after this. It's another little cheeky example where students make a common error, and I wouldn't want you folks to make it. But you can pause the video and do those 2 questions first, and then we can move on to the common error. Right, I hope those 2 questions went well for you. Here's the common error. When we get a question like this looks too easy to be true. I say we could just divide through by sine theta. And if we divide through by sine theta, we end up with 2 sine theta equals 1. But we can't divide through by sine theta because it's possible that sine theta could equal 0. And you cannot divide by 0. So we can divide by a constant, we can divide by 2 or 10 or something fixed constant, but when we're dividing by a variable, we have to be careful if that variable ends up as 0. Therefore, let's go to the question. Rather than dividing by sine theta, we subtract sine theta from both sides, and we end up with that. We then take out a common factor. Both those terms can be divided by sine theta, so we can factorize it as sine theta, 2 sine theta subtract 1 equals 0, and that gives sine theta equals 0, or the bracket, which is 2 sine theta subtract 1 equals 0. And then from there, you go on to solve those 2 equations, sine theta equals 0 or sine theta equals a half. I won't finish it off from here because I'm quite certain you know how to do that by now. But please do be careful when you see one like this. You can't divide through, okay, by something which could equal 0. And if you have a look at question 2, parts B and D, on page 221 of the textbook, you'll find that type of question comes into play. Okay, best of luck, folks. Hope it goes well. See you tomorrow.